Alright folks, here's a good old Desmos. It has its own app if you don't want to go to the website, but here's a couple of lines. Again, each equation, the solutions, if you graph them, form a line. There's no exponents on the x or y's, so we call these linear equations. If you have two unknowns and two equations, then there can be one unique solution to both questions at the same time. Now you can just look at it, see, the question is, where do the lines cross? Well, right here. Remember, this visual over here of these lines is logically equivalent to these equations. It's just as good, and you can see it, and we like that. The equations are kind of harder, though, to work with for us, but you can see the answers, right? That's where they cross. Now, can we show that using these symbols, though? Well, I'm going to do this and try to write it real pretty, so you get an example of how a written proof should look. And it's hard to do that with this type of problem because we have arrows and things going on. Now, we'll do it both ways again. We'll do it the addition method. Remember, when we say this method, we're talking about solving for the first variable. So addition method, let's do that. And again, you don't have to add. We could subtract the equations too. It's just adding a negative. Now, if you add these together like this, the x's won't go away, the y's won't go away. So we have to kind of, mold them a little bit to try to make this work, because the goal is to get rid of an x or a y. But you might see this and go, oh man, I don't like fractions. Hey man, they're super easy, especially if you take the number on the bottom and instead of having it written like that, because that's really 10 plus 5, a human plus 5 more, it becomes real easy when you use the fundamental theorem of arithmetic, and instead of representing it like that, write it as a product of primes. Because if you have something over here like this, 21, then you can see that this guy just needs a 7 and this guy just needs a 5. And if you multiply by the number 1, all right, in a smart way, you can fix that. So he doesn't have a 7, so give him a 7. That's the number 1. I multiplied by 1. And this one doesn't have a 5. Okay, give him a 5. 5 over 5. This is the number 1. Multiplying by 1 doesn't change the value. Now look, samesies on the bottom. So you'd have 7 and 5 of these things. What are they? We have that many of these. 1 over 3, 5, 7. It's super easy if you do it that way. I don't know why they teach it such horrible ways in school. Well, they didn't bother to teach you the fundamental theorem of arithmetic. But anyhow, this is fractions. So we're not even doing algebra. This is arithmetic. But if you don't like them, here's what people do. Clear the fractions. You just karate chop these dudes. Hi-ya! You cut them down to size. Well, really, we're doing the opposite. We're going to build them up. Build up their confidence so they're not less than a whole number. I mean, they're like, oh man, I'm not even a whole number. All right, build them up. Right? Just do both sides of the equation. Make everything bigger so that all the values are whole numbers. That's what we're going to do. This is a technique that's done all the time. So if you don't like fractions, let's rewrite this equation in a different way. So this system of equations is equivalent to, well, if I don't do anything to this equation, then obviously this is the same as that. Okay, I'm going to go ahead and put this over here too. I kind of like it like that. Now I kind of have like, it's contained. It just looks nicer to me. We're going to take this one, and how do we get rid of the fractions? Well, this wouldn't be a problem if they say this was a 12, because 2 goes into 12, right? And this wouldn't be a problem if this was like a 21 instead, because 3 goes into 21 nicely, right? So what we want is to get numbers here and here that are numbers that 2 and 3 will go into nicely. And we can adjust these as long as we do it to all three, everything on both sides. As long as we multiply everything, both sides by a number, we get an equivalent equation. You know, it's the same as like this. If I had 1/2 x plus 1 equals 2, and you want to get rid of this, since there's a 2 on the bottom, you could just multiply everything times 2. The 2 over 2 cancels out, you know, and you just have that. That would give you just an x. And then you have to do it here and here too, right? All we did was make twice as big, twice as big, twice as big. So it's the same question. Basically, we just got closer to it so it looks bigger. Okay? That's what we do in the real world. If something's too small, you just get closer to it, right? So that's what we're doing. But what number do I pick? What am I going to multiply everything by? Well, what's the smallest number that 2 will go into? You could be like, well, it'll go into 4. You know, to turn a 1 into a 4, I could multiply by 4, right? Okay. I could, if I multiplied everything times 4, if I did that, okay, 2 goes into 4. What about this one? Well, 4 times 2 is 8, but 3 doesn't go into 8. That's not how you want to approach this. You want to do it the same way you would approach adding fractions. Check it out. Let's look at this little guy separately. This is something y'all need to be able to do. So let's get us a new page. I wonder how I do that. I'm going to try this. Side note, side quest, right? Side quest. Boom. Clearing fractions. Now, the fundamental theorem of arithmetic should help you. Oh, now I wonder how do I paste? Apple pencil, how do I paste? So I go here and go, oh, there we go. Yay. Okay. Well, check it out. To get rid of the 2, 2 goes into 2, right? If you multiplied everything by 2, 2 over 2 cancels. And here you would have a 2 times a 2. I'm not going to turn it into 4. And then the 3 on the bottom. So all I did is distribute. I'm distributing. And then I have equals 2 times 1. I'll just go ahead and write 2. Right? So, yeah, the 2 got rid of that. Cool. But we still have this one because 3 does not go into this. These 2's are prime. Right? So, well, half a success though. So now these are equivalent. They have the same set of solutions. To get rid of the 3, I can multiply everything times 3. Okay. So 3x and 3 times 2 times 2 over 3. And then 2 times 3. I mean, the whole point of doing this was so that the 3 over the 3 would cancel, right? And I shouldn't have said cancel. This is the number 1, and we're multiplying by it. We can choose not to do that. But that's how we get rid of that, right? So if you want to, those go away because it's just multiplying by 1. And 2 times 2 we'll call 4. And 2 times 3 we will go ahead and call 6. Okay, so what did we do? To get rid of the 2 and 3, we multiplied by a 2 and a 3. Yeah? Of course we could have done it in one step. Y'all like that. Y'all would probably do this. Here's what y'all would do. And it works, but it's not the best method. You'd realize the smallest number that 2 and 3 both go into is 6. And if you multiplied everything times 6, you'd say, well, okay, 2 goes into 6, 3 times. And this one, if we multiply that and simplify, there's another problem y'all could do. You could either go 6 times 2 is 12 and then divide by 3, but now you're going all the way up to 12. Don't do that. All right, because what are we doing? It's a 2 and a 6 over 3, right? You can either multiply these and make big numbers, or you could do this first and make smaller numbers. You got a 2 here, and 6 over 3 is 2. See, I went down to the 2 instead of up to 12 by dividing, then multiplying. That's how you want to do your math. Don't do it the hard way. We're just so trained to do everything the hardest way. Make the numbers all huge for no reason when you don't have to. So the easy way to do this, right, is divide before you multiply, as long as it gives you whole numbers. The other problem here, I don't even have that many fingers on one hand. So like I said, don't write 6. 6 is the same as this. This is another way of writing 6. And these are small. And it's easier to look at it and go, the 2's will cancel, the 3's left over. Right? And here, the 3's will cancel, and the 2 times 2 gives you a 4, right? And then you have your y. And then here, 1 times 2 times 3, I'll go ahead and say 6 now. I might just leave it like that, honestly. And this, I might just leave it as 2 times 2. For y'all, it might be a whole lot easier if you do the opposite of what we taught you all throughout the last 12 years. Don't hide the structure. 4 is not a number. It's a combination of 2 numbers. It's called a composite number. So y'all can get your arithmetic down instead of doing it the hard way and thinking of which symbol represents a quantity that happens to be evenly divisible by the quantities that these 2 symbols represent. That's a lot of processing, and it's not necessary. Just think about it. If you do it this, come here. If you do this, you have to know how many fingers this symbol represents, how many fingers this symbol represents, and how many fingers this symbol represents. This means that. This means that. And this means that. That's what they are. Do we even need to know all that? Well, look, if you use prime factors like this instead, well, guess what? Now it doesn't matter. We don't even need to know any of this. It doesn't matter. We don't need to know that, because when you multiply these and you have a 2 and a 3 and the 2 on the bottom, it does not matter how many fingers that symbol represents, as long as it's not 0. This is the number 1. So when you do it this way, you can solve these problems without needing to know so much. You can know way less. We want to answer the question, and only the question. We don't want to have to answer 1,000 other questions that weren't asked, right? So why get this symbol involved at all? We don't need that symbol involved. This problem does not have that symbol in it. Why introduce a new symbol? Well, we could just use the symbols that are already present. It makes things so much easier. Okay? Now let me give you another example, because this one is too simple. You don't want to just take this number and put them over there. Okay, so here's another example so that you can get it. If I have this and this, and I want to clear the fractions. Well, first off, this is base 10, and you're really hiding a plus sign, right? This is not 1, 5. We call it 15 because there's a hidden operation, a function, if you will, where the symbols, these 2 symbols go into the function, and what comes out is really this but then we abbreviate that by writing this. So the function doesn't even have a symbol that represents it, but there is a hidden operation here. This means plug the 1 and the 5 symbols into a function that gives us that, and then don't bother to write that. Okay? That's what's really going on. That's awful. That makes everything so much harder. So instead of having all that encryption and coding, rewrite it, right? 15 is better represented as a 3 times a 5. And 21 is better represented as a 3 and a 7. Because these are primes. There are no other numbers that divide into them. So you don't want to just multiply everything times a 3 and a 5 and a 3 and a 7. You don't want to do that, right? What do you need to do? I need to make these go away. They both have a 3, right? So I only need to do the 3 once because it's going to go here and here. So the 3 over 3 goes away and the 3 over 3 goes away. Again, you don't have to do all of these. You don't do this and this. Don't do that. We don't need 2 3s. Okay? That would make everything larger than we need. We only need 1. There's only 1 on the bottom. Okay? So that you don't oversimplify. We need a 3 to get rid of the 3's, and we need a 5 to get rid of the 5, and we need a 7 to get rid of the 7. It's that easy, right? Now, when you multiply them, distributive property, right? Here, check it out. If you want me to write it out, all right, 3 and a 5 and a 7, and a 3 and a 5. A 3 and a 5 and a 7. And then 1 times a 3 and a 5 and a 7. Okay. You can write all that out, but the whole point of doing this, well, an extra advantage is you could just look at it. 3 over 3, it doesn't matter how many fingers that's worth. That's the number 1, and you're multiplying by the number 1, and you don't have to do that. You see, so you don't have to write that down. And the 5 over the 5, same thing. That's the number 1. Okay, so you can just look at it and go, those cancel, and I'm left with that symbol. Doesn't matter how many fingers it's worth, but that's what we got. So hopefully you can just look at it and go, the whole point was to get rid of those. This is the thingy that's left over. Cool. And here, that goes away, and the 7s go away, and this is what's left. So instead of writing 1 times 1 and so on, just you don't need to write all that. 3's cancel, 7's cancel, and you're left with the 5. So 5y. Right? It's way easier. That's super easy. It's probably the easiest way to do it. And then this times 1. And you know what? I'm going to leave it like this. I don't know what, I'm not going to encode this. I'm not going to say I have 3 boxes of 5 things, and each of those 5 things is a box of 7 things, right? I'm not going to turn this into some huge number. No way. I don't have time for that. Whatever it is, this is just as good of a name. It's actually better. So that's how I would clear the fractions. Don't multiply this out. Don't ever do that. Leave the structure. The structure gives you more options, more possible paths to solve the problem. That's how you do it. Of course, it's related to adding fractions, but it's the fundamental theorem of arithmetic. The first thing they should have taught you. You would have discovered it on your own if they'd just given you any time at all to think. All right. Again, here's an example. Here's 12. No, it's 1, 2. No, we call it 12. Why is it 12? Because, again, we're hiding the plus sign. How many is 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, base 10 says we should say it's the same as this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 2. That's all we're doing. And that sucks, right? But this is how we represent our numbers. We only have 10 symbols, and so any quantity larger than 9, we have to have a rule for combining these symbols to represent them. So we have to do that. We have to use this. But when we're doing arithmetic, we don't have to do that. If we avoid it if you can. Because by rule of samesies, if you had time to play, you might be like, instead of a human's worth of fingers, you could do this thing, right? 3, 6, 9, and 12. Why would we do that? Well, because these are the same. Those are all the same. Now instead of 12 things, I have 1, 2, 3, 4 things, right? Yeah. I have 4 things, and each of those 4 things is 3 things, right? But hey, actually, yeah, 1, 2, 3, 4. But you know what? This is the same as that. So really, I have 2 things. 2 things. And each of those 2 things, each of these 2 things has, oh man, oh no, I broke it. This one? Oh boy. All right, Apple, how do I fix it? Come back to me. Close. There we go. Yeah. So I have 2 things, and each of those things has 2 things, and each of those 2 things has 3 things. 4 times 3, this is 12, you see? So you might have discovered the fundamental theorem of arithmetic, oh come on your own, just by organizing things in the simplest manner you can. The rule of samesies instead of piles of 10. Okay. Okay, why is it typing over there? Stop that. Go away. How do I make that go away? Oh, sorry, I'm new to this. Okay, anyhow, I delve into this because, again, everything we're doing, why are you doing all this? Leave me alone. Go away. Oh, that was the side quest. Maybe that'll go away now. Let's go back to our problem. Where'd you go? Here we go. All right, clearing the fractions. So we want to get rid of fractions. So we got to get rid of the 2 and 3. And yeah, you could do this, right? Y'all probably should at this point. And the 2 over the 2 cancel out, and you have a 3x, right? So you put right here 3x. And the 2 times the 3 times this, so don't go 12, no. And then divide, you go, the 3's cancel, and I'm left with a 2 and a 2, which y'all can call 4 if you want, okay? And then this times 1, just multiply everything by these. And y'all like to call that 6. Fine. But I mean, you could just eyeball it. Oh man, come on. Can't y'all just eyeball that? You don't even have to write this down. Can't you just, I mean, after you do this method a few times, it's so simple, you could just go straight here, right? Like, you know, you got to get rid of those symbols, so put those symbols here. Okay, great. All right? So, sure, all we did was make everything 6 times bigger, so this is an equivalent equation. The solutions to this are the same as the solutions to this, meaning they're the same line. Okay, but there's no fractions. Yay! Well, now it's almost like that first problem. Now we got rid of fractions. We still have a dilemma, though. If we're doing the addition method, the x's and the y's, neither of them go away. Oh, no. Well, we can do the same trick to fix that, right? If I want the x's to go away, I could multiply everything times negative 3, because negative 3x and 3x, they would go away. Or if I wanted the y's to go away, I could multiply everything here by just positive 4, because 4 times negative y, that would be a negative 4y, and a 4y makes them go away. So it doesn't matter. So like on a quiz or something, they might have you like state which variable you're going to solve for first. Who cares? Just pick one. It doesn't matter. So anyhow, let's manipulate so that we can use the addition method. I'm going to make x's go away, I guess. So here's one of the big advantages of having a digital pad that you can write on is the time you save writing. So I'm going to keep, oh, I picked the wrong one. That's okay, watch this. Instead of rewriting, I'm going to copy and paste. So obviously these are equivalent because they're exactly the same thing. And then this, to make it match this, that's where I'm going to multiply everything by the minus 3. Okay? So if I do that, as long as I do it to everything, I'll have an equivalent expression. So minus 3x, and then minus times a minus is a plus 3y. Okay? And don't forget this part. I often do that. I'll forget to multiply by this number by itself. That's an easy mistake to make. Real easy. Okay, so these are the same two lines as these two lines. Okay, they're the exact same lines. Okay, and you can see that, look, here in Desmos, check it out. If I take this blue line and I multiply everything times 3, watch this. Multiply the first one times 3, multiply the second one times 3, and then multiply the 2 times 3. See, it's the same line. Well, they changed its color, but you see? Same line, same solutions. All right. Now we can do the addition method. Boop. So 3x minus 3x go away. 4y and 3y give us a 7y. 6 minus 6 is 0. So if 7y equals 0, then obviously y has to be 0. And that's half the problem. Now we need to figure out x. And we can, now that we know y is 0, replace 0. Y with 0. You could plug it in here, or you could plug it in here, or you could plug it in the original one. It doesn't matter because these are all equivalent. So you're going to plug it into the simplest one possible. And these numbers are big. You know what? The simplest one I see is this guy that we started off with. So that's the one I would choose. You know, I'm not going to pick a hard one. So to tell my reader what I'm doing, I would say substitute y equals 0 into, oh wait, how do I paste? Paste, there we go. Substitute y equals 0 into that, and that gives us x minus 0 equals 2, or x equals 2. Boom. Okay, now we need to state here is our answer, because the answer is a coordinate and we need to give it as a ordered pair, and then check our work, make sure it works. Check work. Now, these are all equivalent, right? But we could have made a mistake, right? So if you really want to check all your work, you want to use the original problem. Make sure your answer is an answer to the original question. Right? Here's the original one. Here's our 2 and our 0, right? So what we're going to do is replace the x with 2 and replace the y was 0. Oops. Okay. If we do that, what do we get? 1 times 2 over 2. 2 over 2, that's just 1, isn't it? And anything times 0, these are hard to see. 2, 2, we're multiplying by 0 here. All right. So here, anything times 0 is 0. And then we have equals 1. Yes, 1 equals 1. How about this one? 2 minus 0 equals 2. Yes, that's true as well. Boom. Now, is this nice enough to turn in for a reader who's not going to... They can't read your mind. They can't hear you. All they're looking at is your paper. So if this was the original question, I can see this is what they did to get this. And this symbol is connecting this to this. So I can follow the train of thought, the flow of logic. And now from here, I can see they kept this and they got this by doing that to this stuff. Okay. And addition method here, they got this equation by combining these, and that gave us that, and then substituting into the original equation, okay, that gives us this equation, which is just this, and putting them together. That's, I mean, it's not pretty, but it's logical, it's legible, you know. I wrote this stuff really ugly and fast, but it's readable. This is definitely a Y. It's not a Yex. Okay. This is definitely a 2. Okay. This is definitely a 4. All right. Not a 9, because if you write your 4s like this, you do it fast, it might kind of look 9-ish, so don't do that. Some people write 9 as a key, like it is on the keyboard, looks like a lowercase g. That totally confuses me. Now, if I look at it on the keyboard and I see it, I totally see a 9. But when it's written by hand, it looks like a G, so don't do that. This is definitely not a 1. It's a 7 for sure. Okay. So it's ugly, but it's totally legible. Nothing's ambiguous. Yay. Now that's one way to do it. Let's do it the other way. Okay. This is how you write it out, right? Let's see how few steps and how quickly we can do it if we're just trying to get the answer for ourselves and we're not interested in telling anybody else how we did it. We just want it for ourselves. How quickly can I do this in my mind? Here's the question. Well, I really don't like the fractions. So I might have to, just to make it easier for my brain, I will do this one step. Multiply everything by the 2 and the 3. The 2's cancel. I'm going to get a 3 left over. Here, if I hit it with a 2 and a 3, in my mind, the 3 goes away, and the extra 2 hits that 2. Right? So again, in my head, I'm hitting everything with a 2 and a 3. 2's cancel, left with 3. Boop, boop, boop. Uh-oh. This next one, the 3's cancel. I got 2 2's. Okay. And then the 2. So I don't write down any of that stuff. My goal is to write down as little as possible, right? Okay, and I would go ahead and write 6. Why would I put a 6 instead of a 2 times 3? Because I'm aiming to do the addition method. And when you add, you don't want to add this to that, because then you're mixing symbols. We only have 2 operations. Right? If you're going to add and multiply, you have to go to this. So that's why I went ahead and put it that way. Okay, so one step in my head, I write this down so I can stare at this. Okay, I know I don't have to add, I could subtract, right? So without even writing it down, I will, in my mind, I'm multiplying everything times 3 first, okay? So this minus 3 times that makes the x's go away. So I know that. So I'm not going to write anything about x's. But in my head, I know that that's what makes the x's go away. So I'll 4y, and then if I do minus a negative 3, right, that's a plus. So in my head, I'm doing this minus 3 times that. This minus 3 times that. And hopefully I catch the minuses, because 4 and 3 is going to give me this 7 here. And then over here, 6 minus 6, 0. So the fractions make it difficult. I got to get rid of the fractions first, because my brain doesn't like it. Now that I got this guy, I can just look at this. Once I figure out in my, with this minimal steps, and I know y is 0, I can just look at this and go x equals 2. Boop. Okay. Now let's try it again, writing it out where instead of clearing fractions, let's keep them. Let's work with the fractions. Let's see if it's how much harder it is. Right? We didn't have to do that. Okay, well, let's say I want to get rid of these. I'll pick that because these are easier. 1 and 2 is smaller than a 2 and a 3. Fine. Well, I could just, if I'm writing everything out, to be beautiful for the reader so they can follow what I'm doing, I'm going to keep the fractions. If I want these to match up, I'll multiply everything by a negative half, because that's what cancels with a positive half. So hitting everything with that, I got negative half x. And honestly, I should have done this. How do I select this guy? Oh, look at that. Because I want it to be pretty, right, for my reader. This is kind of ugly. Hitting everything with a negative 1/2. Boop. Okay. Negative negative is a positive. Okay. And then equals a negative 2 over 2. Notice how I wrote this. I could have written this, y over 2. But I went ahead and said this instead. Sometimes I do this. Oops, there, I forgot the y. Sometimes I do this. In this case, I do write this extra 1 because I want to see the coefficients by themselves, because that's what matters. Okay? That's the most important part of this. So that's why I'm writing it like that. It's better, okay, to do that in this case. Okay. Now, if I add them, those go away. But now, oh, I have to add fractions. Oh no. They're not the same and all. In my head, I can look at this and go, this one needs that and this one needs that. So in my head, I can be like, there's really a multiplying by 1. I'm multiplying by 1. And now they both have a 2 and a 3, right? And in my head, I can go 4 and 3 is 7. And 2 and 3 gives us a 6, right? You should be able to do this in your head. 2/3 and a half. Y'all might be like, well, the smallest number that 3 and 2 goes into is 6. So I'm aiming for 6. 2/3, 2 out of 3 is the same as 4 out of 6, and 1/2 is the same as 3 out of 6. And therefore, these are 7/6, right? So we could do that, no problem. 7/6. Should I have left that for you, for the reader? Right? Let's go ahead and do that. It'll be like side quest. 1/2 and 2/3 is the same as 3/6 and 4/6, which is 7/6. Doo-doo-doo-doo-doo, and a little star, right? Cool. So adding, those go away. This is 7/6 y's, and I forgot my minus sign. Boom! Almost. That was almost a big problem, because from then on out, all the work I do would be totally wrong. Now, how did I catch that? Well, I remembered before this added to 0, remember? Like zeros, right? Y equals 0. But you want to have mental checks every step of the way. But anyhow, 1 minus 1 is 0. So instead of 7y equals 0, it's just 7/6. Still, y equals 0. Now, how do we get x? Substitute. All right, so we could do this. Boop. I'll be like, boop. Well, x minus 0 equals 2, therefore x equals 2. So you could just leave the fractions there. You don't have to do that. If you're okay with adding two fractions that have the first three smallest numbers in existence, you don't need to clear the fractions. You know what I mean? That's just extra work that doesn't need to be done. Okay? So there you go. All right, now let's do the same problem again with substitution method. Here we go. Here is the question at hand. Where do these lines cross? Boop, 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 boop. Okay. Substitution method. Okay. I'm going to go ahead and put this one here too. I like it like that. Okay. So instead of adding them or subtracting them, nope. We're going to shove one of these into the other. So first off, you kind of need, I'm going to go ahead and do two steps here. One, I'm going to go ahead and clear the fractions, right? So there we go, boop. I'll go ahead and do this in a different color. Multiply by the 2 and the 3, and then what do we get? The 2's cancel, I got a 3. Here, the 3's cancel, I'm left with two 2's, which we like to call 4, and then 2 times 3 times 1. So doing that, and then this guy, since I want to substitute, that's the goal, I need to get one of these letters by themselves. If I move the y over, I get x equals, right? You could do this. Here's what I'm doing in my head. All right? If you want to do that, you can. I don't like it. It looks like scratch work to me. Because if you don't write that down, but down here you just, say x equals 2 plus y, I know that these are equivalent. I can tell that, oh, the y is gone, but now it's over there. That's a simple thing, right? You don't need to do that for me. Okay, so these are the same two lines. Why did I do this? Because now I can substitute. X is this, right? So replace the x with this guy, and then, right, what do you get? Boop. Notice how I'm doing all these arrows and stuff? It's like, how do I visually write down my flow of thought with standard mathematical notation and such? Okay? Use the right symbols for the right things. This means combine the equations, right? This means this question is equivalent to this question, right? This means this quantity is the same value as this quantity. They represent the same number of fingers. This is one of the few times that I use an arrow as an official notation. Y'all stick arrows. Instead of an equals, you'll put an arrow. Don't do that. Instead of this, you'll put an arrow. Don't do that. It's like pointing and grunting. But here, combining these two via substitution, gives me this result, right? And I might, substituting those, therefore I get, okay, that's like a this, but telling you where I went to. See how messy this is? This is why we have matrix notation, which I'll show you in a minute. So, okay, great. Now, substituting. So if we put those together, combine the two questions to make a new question, replace the x with the 2 plus y. I still got a plus, and then 4y equals 6. So that's what I did. I combined them, and the point of this was to eliminate the x, replacing the x with an expression that doesn't have x. And I end up with something that only has y's. Okay, now I can get my y. I can solve for y. So distributive property is really multiplying, see? Pluses and multiplying, mixing operations. Distributive property, great. 3 times 2 is 6. 3 times y is 3y and 4y. These are the same. This is the same as this. And then I can do 3y and 4y is 7y's. Subtracting 6 from both sides, I get 0. That's the same thing as y equals 0. Yay! So that's a lot more work to get the first variable. Again, the substitution method involves way more arithmetic, and you're more likely to make mistakes. Once you have y equals 0, again, the rest of it's the same, right? Substitute y equals 0 into the original question. So we've done this several times already. Pow! All right. So the y equals 0. Do-do-do-do-do-do. That gives us x minus 0 equals 2. So therefore, x equals 2. And make sure you write your answer as an ordered pair. Bow. And then, of course, like we did before, check your work. All right, I think we've beat this simple problem to death every which way we possibly can. So what you do is you do problems like this over and over and over again. You know, make up your own problem here. Just go here, you did this problem, okay, change it to, okay, 5. And then over here, and throw a fraction down here maybe, I don't know, 2 thirds. There you go. Brand new problem. Now there's more than one fraction. There's fractions in both. You know, how would you approach that? You know, well, okay. Instead of clearing fractions in one, you might clear them in both. Let's take a glimpse of this real fast. So the next problem can be different. Here, 2 thirds, and then a minus 1/5 equals 1, and then 1/2 plus 1/6 equals 1. All right, if I'm going to clear these fractions, because I don't like them, to get rid of a 3 and a 5, I would hit everything with a 3 and a 5. The 3's cancel. 5 times 2 is 10. Okay. Here the 5's cancel, and I'm left with the 3. And then 3 times 5 times 1, y'all like to write as 15. Great. This one, I got to get rid of the 2 and the 6. Well, the 6 is really a 2 and a 3. That's what that is, right? So don't multiply everything by 2 and 6. No. Okay? Realize that the 6 is really a 2 and a 3. All I need is a single 2 to get rid of the 2 on the bottom, and a single 3 to get rid of the 3 on the bottom. Right? 6 is the smallest number that 2 and 6 goes into. right? If I put a 6 here and a 6 there, 2 goes into that, 6 goes into that. But pretend that this is a bigger number where that's not obvious. Then this approach, it doesn't matter how many fingers the symbols are worth. 2 over 2 goes away because it's just the number 1. Multiplying by 1 doesn't matter. And you're left with a 3. Oh, I don't want to use that. Here, 3. Okay. Here, since this is 2 and 3 and that's a 2 and 3, their ratio is 1. I'm just left with the y. And 2 times 3 times 1 is 6. Okay. Notice how I try to keep my x's and y's lined up. There's a good reason for that. So I cleared the fractions. This is my new question. It's the same question. Okay, if I want to get rid of something, this is a huge number. I don't want to deal with it. Here's a little one. If I hit everything here with 3, okay, if I do that, then those will match up and I can do addition method, right? So I'm going to keep you the way you are, just like the way you are, yeah. So 3 times 3 is 9, and 3 times y is 3y, and 3 times 6 is 18. Great. Now if I have a reader and I want to show them the steps, I would do this step and then this step, and then I would say, okay, nope, they're not equal. I'm good. Now I've set myself up to do the addition method, right? To get what? 10 and 9 makes 19. Now the y's go away. That was the whole point of this dude. Why did I do that? Because I noticed I could make these go away if there was just a 3 there. So I put a 3 there. All right, and then, yeah, the y's go away, and I get 33. Oh, that's a huge number. Okay, so the x is 33 over 19. And that's prime, so this won't simplify, right? Great. Now that I have my x, substitute it in. 33 over 19, right? 33 over 9. You could put it here, or you could put it here. It doesn't matter. You could put it here or here. Any of them will work. And then solve for y. It's just ugly fractions, right? Now, if I'm doing it for myself, I wouldn't write this down. I'd know that a 3 there will make it work out. So I would just do that in my head. I would just be like, okay, 3 times 3 is 9, and then add the 10, and I would get this. So I would go straight here, because I would look here and go, I got the 3, the y's go away, and then here I'd hit that with a 3, and I'd be like, okay, 18 and 15. I would just go straight here if I was trying to just do it mentally. Okay? And just for the fun of fractions, let's do it. Let's find our y. So if I'm going to choose which of these equations to plug the x into, which one do I choose? Well, I don't know. This one has big numbers. I don't like big numbers. Hey, look, this one has pretty small numbers. I like small numbers. These have fractions. Then we're combining it. Yeah, look, I would pick this one here. Why? Because the numbers are really small. That's what I would do. So find y by substituting x is 33 over 19 into this dude. Pow! All right, so what do we get? 3 times 33 over 19 plus y equals 6. To solve for y is 6 minus this number. And as a mathematician, that's the answer. Everything else is arithmetic. But if you want to calculate, all right, I don't need a calculator. it'd be nice to have one because 19 is a huge number and it's prime, so I can't really simplify that. That kind of sucks, but that's okay. Check it out. What do we mean by simplify? We mean get rid of the minus sign. Fine. So what I can do is we need samesies on the bottom, and 19 is a number. It's not the product of any other numbers. It's its own prime. It's huge. So the only thing we can do to combine these is hit this with a smart 1. Multiplying by the number 1. So I haven't changed the value. So what do I have? I got this many of these, right? The 19 on the bottom. And then I have this many of, here, I'm going to do this, of the same thing, right? The denominator is 19. So what sucks here is this. What the hell is 6 times 19? And because I can't break 19 down because it's prime, it's just rote calculation. You see, if it was 18 instead, I would be like, I don't know, but 18 is the same as a 6 and a 3, right? Yeah? And then I could do 36 times 3, or I could be like 6 is 2 times 3, right? I could do that, and this gives me all kinds of different possible paths to figuring out what is this equal to. I could do 4 times 9 times 3, or 27 times 4. See how revealing the underlying structure gives you lots of different choices for finding the answer. That's what you want to do. But this particular problem sucks because 19 is fundamental. It's a prime. There is no structure to reveal. So we are simply stuck with this right here. We have to do 6 times 19, right? That's the only way to do this. Why? Well, because we have this many of these and this many of these, right? Well, let me write it this way. We have this many and this many of these. I can write it like that. This is the thing we have. This is how many of them we got. Oh, I'm missing a 3. So, okay, this is just painful arithmetic. This is what computers are great at. This is the only path we could do to simplify this, because this dude is prime. Okay, so how do we do this? You do this thing, this algorithm, right? 9 times 6, and we memorize that's 54. And then 6 times 1 is 6, plus 5 is 11, right? Okay. And then 3 times 33, we'd be like, boom. I'm sure there's number tricks. 3 times 3 is 9. 3 times 3 is 9, 99. I hope you can do that in your head. All right. So that is this of these, okay? So 114 minus 99, that's 15 of these, okay? This is prime. This is really a 3 and a 5, neither of which are 19, so there's nothing we could do. It's 15 19ths, and that is what y is. See how I started off with y is this value, which can be rewritten like this, which can be rewritten like this. This is a chain equality, but it started off with the variable y is found to be equal to, and so for brevity and closure, I like to remind myself the beginning of the sentence. This is what y was. Now that I know what y is, we got, what was our x? 33 over 19. 33 over 19. Okay, Dexter, calm down, puppy dog. And then 15 over 19. this is the coordinate. And then, of course, you want to check your work, right? Now, you could look at, if you didn't want to do all these fractions, which you should do for practice, watch this. There it is. Is that right? Huh? 2.5 3/4. That's not what I got. Is that the? Oh, this is a different question. Well, that's why. Let's put the right question in here. So I know what y'all are doing. You're gonna look at this and be like, all right, let's put it in 2/3 and -1/5 and 1. So, sorry, y'all, my dog is really wanting to be in my lap. 2/3 and, oops, -1/5 -1/5 equals 1. Yeah, and now 1/2, 1/6, and 1. Okay. 1/2. Oh man. 1/2 and -1/6 and 1. Is that right? 1/2 -1/6. 1/2. Oh, it's +1/6. Okay, so let's try it again. +1/6. Boop, boop. Delete and plus sign. There we go. All right, so where did the lines cross? We just did the math. Well, is our answer the same? Oh man. Well, look, here it is. Ooh, those are decimals. Well, we have fractions. Are these the same? Well, this coordinate, this is not correct. This is an approximation, right? They round it off. So, check this out. What was it? Don't look for your handheld calculator. 33/19. And what was the other one? All right, puppy dog, come on, hop in my lap. Quit being annoying. Good boy. Pow. 15/19. Okay, fine. 15/19. What was this over here? Boop. Pretty close, right? See how they rounded over here where the coordinate is? 684, whereas over here we have even more decimals. And see, they're lying. See how they say 33/19 is equal to this decimal? That's just a straight up lie. That's not what it's equal to. It's approximately equal to. 33/19 is exact. And look how many pin strokes it took. 1, 2, 3, 4, 5 pin strokes. Over here, though, that's a whole lot of symbols, a whole lot of pin strokes, and it's not even true. It's a lie. That's an approximation. Use your fractions. This is math class, right? We want precision. Okay, so the fractions are ugly. This is why we use calculators. That's why I don't want to teach you to be a calculator, right? I intentionally use small numbers. And you can see even when we picked 1, 2, 3, 5, 6, the biggest number I chose for this problem was 6. Just because I was trying to be more diverse than before with the fractions. Why did I pick them? Well, these are both prime. This is prime. I didn't want this to also be prime. I wanted something a little different. So I wanted to have at least one denominator that was a combination of two primes. And I wanted one of them to be shared by one of the, so that you get some idea of what you can do. There's more possibilities here. If I had to put a 7, which is prime, then these are all just primes. They may as well be any symbol at all. It doesn't matter. This being a combination of two primes and having, including one of the others, that's a different, there's different possible paths you can choose to take, right? And oh, I'm so tired, so I probably end this, and next time we will come back, think about this. What if you have irrational numbers? Right? Something like this. E. Yeah, we're going to use E. E is Euler's number, if you haven't heard of it. I know it looks like Euler, but it's Euler. Euler's number. It is defined to be 2.71 ... Okay? Super important, more important than pi. And because it's a letter, it messes you up. It's not like A or B or C. No, these are unknown constants. It's not like an X, Y, Z. These are variables. They're unknown and they vary. This, like pi, is a fixed value. It does not change. So the symbols that you have, 1, 1, these are fixed known amounts of fingers. So is this, and so is this. And actually, we'll get to this as well, square root of -1. Those will be your digits, okay? Those are the names of fixed known quantities. So something like this is a good question to do. It's the exact same question. Here's two lines, where do they cross? Right? Every single problem I'm giving you, here's the name of a number, name of a number, name of a number. So what? This is a known amount of fingers, known amount of fingers. We'll do with that one, and then we're going to do the real one. Here's a known amount of fingers. I just didn't tell you what it is, a known amount of fingers. And here is a known amount of fingers. And here's, oops, this. We're going to solve this next, because this is every single algebra problem you could do. Where do any two lines cross? Instead of where do these two lines cross? This is algebra. This is the only problem you should have to solve, right? Yes, your coordinate answer, it will have these 6 symbols combined with addition and multiplication, but that will be the answer to every single possible question of where do these two lines cross. That's what we want to do. Then we don't have to do any arithmetic. Blah, blah, blah. Arithmetic is what makes everything hard. And computers are great at that, okay? Nowadays, computers are even great at algebra. But, you know, let's go back a few decades. In which case, this is all they should have taught. Why would you bother with putting numbers there? This is a number, and it could be any number you want. So it makes math so much easier. All right, anyhow, till next time, that was part 2. We'll do a part 3. I'm going to smash this quiz to death so that y'all can do this. It's the hardest one.